One additional piece of information or a question that we should ask here is we saw for the ideal op-amp that R input was infinity while R output was 0. This is for the ideal open loop op-amp. The question is it good or bad to have high R input? Is it good or bad to have low R out? So should we, when we design an amplifier circuit, should we design it so that we have high R input or low R input? Should we design it to have high R output or low R out? So let's try to think about this question, because this is a fundamental and important question. Let's think first about R input. In order to answer this question, imagine that we are going to connect, we have an amplifier circuit that we represented by a block. It has 2 input terminals, 2 output terminals, and imagine that we are going to connect this amplifier circuit to a source. And any source, let's say Vs, and any source, by default, it has an internal resistance. Let's call the internal resistance of the source Rs. So practically speaking, any source, it has an internal resistance Rs. So now, the amplifier, it has an input resistance. This input resistance can be represented, or it is equal exactly to the Thevenin equivalent resistance looking from this side, looking between these 2 terminals. So our input here is the same as R Thevenin. So we can replace our op-amp or our amplifier by a Thevenin equivalent resistance, which is equal to the input resistance of the amplifier. This is Rs and this is Vs. So now, let's ask ourselves, is it good or bad to have high input resistance? You remember from the voltage divider rule, the voltage that will come here at the input of the amplifier, let's call it V input. The voltage V input at the input of the amplifier equals what? Equals Vs multiplied by R input over Rs plus Rin. So now, if the input resistance is small, let's imagine that the input resistance of our amplifier is small. What will happen? If the input resistance is small, most of the voltage, most of the source voltage will go to the resistance Rs, right? According to the voltage divider rule, most of the voltage will go to Rs. For example, if our input is small, 0.8, for example, 0.8 Vs will come here at Rs, while only 0.2 Vs will appear across the amplifier. So you will waste 0.8 of your voltage, of your source voltage, across the internal resistance of the source. And only 0.2 will be amplified. Only 0.2 of your source voltage will go to the amplifier and will be amplified. Of course, this is not efficient, right? Because now you want to amplify your source voltage. So it doesn't make sense that you waste big part of it on the internal resistance, and only the part that will be amplified is the 0.2 of Vs, 0.2 Vs. This is the only part that will be amplified. But as our input increases, as the input resistance of the amplifier increases, what will happen? More voltage will come to the input of the amplifier, right? As our input increases, more voltage, more ratio of the source voltage will go to the amplifier, will be amplified, right? Until our input reaches infinity. If our input reaches infinity, then all the voltage will go to R Thevenin or R input. So Vs, all of it will go to the input of the amplifier, while Rs will not take any voltage across it. So if R input is infinity, this is the perfect situation, because it allows you that the source voltage, all the source voltage will be amplified. It will go to the input terminals of the amplifier and it will be amplified. And nothing will be wasted on the internal resistance of the source. So it's always better, as an engineer, when you design an amplifier, it's always better to have high input resistance. If you can make it infinity, if you can make the input resistance of your amplifier infinity, that would be the ideal case, because all the source voltage will go to the input terminals of the amplifier without losing anything across the internal resistance or across any resistance that is connected here. Let's do the same argument for the output resistance. Okay? Again, when you look from the outside here, you can calculate the Thevenin equivalent resistance and Thevenin equivalent voltage of the amplifier from the output terminals, and you can represent your amplifier as R Thevenin, which is the same as R output, and V Thevenin. And this is supposed to be the output voltage of the amplifier under open circuit condition. So under open circuit condition, the output voltage of the amplifier will be V Thevenin, right? So V Thevenin is the output voltage under open circuit condition. So you can represent the amplifier as an equivalent circuit of R Thevenin and V Thevenin, where V Thevenin is the output voltage under open circuit condition and R Thevenin is the output resistance. The question now, is it good or bad to design this output resistance to be low? Should we design the output resistance to be high or low? This is the question. So again, imagine that you are going to connect the terminals here of the amplifier to a load, like a TV, like a computer, any load. So you are going to connect it to a certain load, RL. Okay? In this case, the voltage that will go to RL, we'll call it V out. This is the voltage that will go to RL. Again, according to the voltage divider rule, the voltage that will go to your load, V output, equals V Thevenin multiplied by RL over RL plus R out. And R out is the same as R Thevenin. This is the voltage divider rule. Now let's imagine that your R output, the output resistance of your amplifier, the Thevenin equivalent resistance of your amplifier, let's imagine that it is large. What happens if the output resistance is large? If the output resistance is large, most of the V Thevenin, most of the voltage, the equivalent voltage at the output of the amplifier will go to R out. So if R out is large, if R out of large is large, then most of V Thevenin will go to R out. So for example, 0.8 of R Thevenin or of 0.8 of V Thevenin will go here, while only 0.2 of V Thevenin will go here, which again is not efficient, which again doesn't make sense. Why? Because we use this amplifier to amplify the voltage, and after we amplified the voltage, we wasted the big part of it on the output impedance, output resistance of the amplifier, and the only small part went to the load. This doesn't make sense, right? Because the purpose is to amplify the voltage and give it to the load, right? Not to waste it on some other output resistance. So in order to allow the load to take high portion of V Thevenin, of the voltage of the amplifier, okay, then we should design our output to be low. We should design our output to be as low as possible. If we can make it zero, if we can make our output zero, what will happen? If our output is zero, then we'll end up with a circuit that looks like this: V Thevenin and R load. So if the output resistance of the amplifier is zero, then the voltage across the load will be always equal to R Thevenin. Then in this case, V output will be always equal to V Thevenin, regardless of the load. Even if you change the load, V output will be equal to V Thevenin. And this is, by the way, the case that we discussed before when we discussed the output resistance of the op-amp. We said, since when we change the load, the output voltage doesn't change. When we change the load, when we change the current in the load, when we change the RL, of course, the current is going to change, right? When we change the load and we change the current in the load, V output doesn't change. This means that output resistance of the op-amp is 0. So that was the conclusion. We said that since the output voltage of the op-amp doesn't depend on the load, it doesn't depend on the current in the load, this means that the output resistance is 0. This is exactly the same case. The output voltage is constant only across the load. It will be constant across the load only if the output resistance is 0. And this is the case of the op-amp, right? But if there is an R Thevenin, if there is an R output, then as you change the load, the voltage across the load is going to change. But in op-amp, we found that the voltage across the load doesn't change. Even if you change the load, the voltage across the load doesn't change, which means that we are working in this situation, which means that our output is 0. So here, our output is 0. And this is the ideal case. This is the best situation. This is the ideal case that we are looking for. So as an engineer, again, when you design any amplifier in your life, it's always better to have high input resistance so that it takes most of the source voltage as an input to the amplifier. It is ideal to have our output to be as low as possible so that most of the voltage, most of the Thevenin equivalent voltage of the amplifier goes to the load. And ideally, our output should be 0. Ideally, our input should be infinity. And that's it for the input resistance and the output resistance. And this applies to any amplifier, not only the op-amp, any amplifier that you will see in your life. Okay, we'll see you in the next video.